So let's read the problem. A cable is unwound from a spool supported on small rollers at A and B by exerting a force of 300 newtons on the cable. Compute the time needed to unravel 5 meters of cable. So time needed for 5 meters of cable to be unraveled from the spool. If the spool and cable, so this is the spool, this is the cable, have a total mass of 600 kilograms, and the radius of gyration is 1.2 meters. For the calculation, neglect the mass of the cable being unwound and the mass of the rollers at A and B. The rollers turn with no friction. Okay, so I'm interested in finding the distance unraveled when I pull the cable with a tension of 300 newtons. So clearly when I apply a force, the spool is going to accelerate, right? So if I know when I know the distance this thing has to turn, because I know how much spool is unwound, if I know the acceleration, then I can find the time, right? Or the velocity. But this is not a case of uniform velocity, because clearly there's a tension. It may so turn out that the acceleration is zero, in which case it might be simpler. So let's try to find the acceleration of the spool and use that information to find the distance unraveled. So I'm going to start with the free body diagram. So this is 30 degrees. Okay. There are rollers at A and B, and the effect of the rollers is to supply a normal force. So a normal to the circle always passes to the center of the circle. That's why NB is shown as the way it is here. Similarly, for NA, the force will pass to the center of the circle. Now, is gravity given? Let me check. Uh, yeah, let's just assume that there is gravity. So gravity acts right at the center. So that's about it. So there's no friction force. If there was friction force, which we've not really covered, we'll cover in the next section, then that friction force will oppose motion. So it will be, so if this is turning clockwise, then the friction force here would be in this direction opposing the motion. But right now there's no friction because it's there's no friction that's given in the problem. So given that, let me try to write the equations of motion. So the question is, what am I interested in? Well, I'm interested in the acceleration of the spool. I do not care what the normal forces are. So given that, you've got to ask yourself, what equations can you write? Now there are only three equations. There is force equilibrium in the x, force equilibrium in the y, and then the moment equation. If you do force equilibrium in the x or force equilibrium in the y, you see that normal forces will appear in the equilibrium, because NB and NA are going to be resolved in the x and the y direction. So let's not try to write the fx, fy. Instead, let's try to focus on the moment equation. Can I choose a point on the figure such that I would not have the normal forces coming up in the equation? And you can do that if you choose the point to be the center of the circle, right? If you take moments about point O, which also happens to be the center of mass, then NA and NB will have no effect because NA and B have a line of action which passes through O. So the easiest way of solving this is to do moment equilibrium about O, which is also equal to I O alpha. So the good thing is that there are three forces passing through O: mg, Na, and nb. None of them wouldn't appear in the equation summation of MO because they all have no moments about O. So only force which will come is tension, and that tension should be multiplied with the normal distance. So it turns out that this force here is tangential, right? So this has to be normal, which means that the line of the perpendicular distance from tension to the point about which we are taking moments O is actually the radius of the inner circle, which is 0.8. So T times 0.8 is the moment, right? Force times distance. And I need to put the right sign. So if I'm taking moments about O, I hold the spool at the center and apply the tension. The effect of applying the tension causes the spool to turn clockwise. And my convention is clockwise is negative. So it's negative. Equal to the inertia. So the inertia is always, well, it's given to be in terms of radius of gyration, right? And when I give you the radius of gyration, it means that's the inertia about the center of mass. Center of mass happens to be at O. So what you need to write here is mass times KO square. That's it. Okay, times alpha. Now convention is alpha is, the way it is in that equation is alpha is positive counterclockwise. So let me sub in the values. I have for tension 300. And then 0.8 equals mass, which is 600 times 1.2 square times alpha. So I can solve for alpha, which is the angular acceleration. It comes out to be negative 0.2778 radians per second square. Okay, in other words, what it's telling me is that the spool is turning clockwise, which makes sense, right? The effect of the tension acting, giving a moment of the tension gives a clockwise moment will cause the spool to turn clockwise. So alpha is 0.2778 radians per second square clockwise. Okay, so next step is, well, I need to find the time it takes to unravel 5 meters. So the next step is, given the acceleration, I need to go one level down, which is velocity and then position. Now, in this case, so I'm going to do kinematics. So I'm given that the spool unwounds a distance of 5 meters, right? However, I have, so that is a linear distance move, but what I know is the angular acceleration. Okay, so there's a disparity. What I'm given is the distance in meters, but I know the angular acceleration. So is there a way to relate the two? Well, what you know is that the distance unraveled, delta S, is related to the amount of spin or the amount of angle turned by the spool by this relation. Delta S is the radius times delta theta, right? If I unravel a spool by distance s, then that will be the same as the arc length which is traveled by the spool. Well, in this case, it's going to be the inner radius of the spool. If this is theta, then this is the arc length, delta s. So if delta theta is the angle turned, then delta theta. So what happens is, as you unravel the spool, the angle, the distance ts moved by the spool is equal to the amount of length which shows off from the table. Is the length unraveled. So given that, I can now find delta theta. And again, I'm doing this because I know angular acceleration, I don't know the linear acceleration. So delta s is 5, r is basically the inner spool, so it's 0.8 times delta theta, which is the unknown. So delta theta is 6.25 radians. I have to find the distance, sorry, the time taken to unravel, well, the time taken now so that the spool rotates by an angle of 6.25, right? So what I can now do is I have the acceleration and I have the distance moved. How can I find the time? What's the relation between time, acceleration, and angle turn? There are no forces. There's a relation between your distance over time is not going to give you anything here because it's not uniform velocity, it's uniform acceleration. So what happens, what's the formula for uniform acceleration? There are three formulas, right? V square equals u square plus 2as in linear world, and then v equals u plus at, and then there is s equals v0t plus half at square. You got to find the analog in the rotary world, so it's going to be delta theta is omega 0, sorry, the formula is written like this, I think, in the book. Delta 0 omega 0 t plus half alpha t square. Again, this is only true because the angular acceleration alpha is a constant. If it was not a constant, then you would go from first principle, which is alpha is d omega dt, and then go from there, integrate once to get omega, and then integrate again to get distance. So here in this case, theta minus theta 0 equals omega 0 plus half alpha t square. There's something here. And I think you're given that initial velocity is 0. So delta, this is 6.25 equals half times alpha, which is 0.2778 t square. So you can solve for t, comes out to be 6.71 seconds. Is that clear? So an example of rotation about fixed axis, as I said, is a pendulum. And in this particular section, we are talking about things which basically rotate and translate, but they do not have any point which is fixed. Okay, so the equations clearly become more complicated. And I'll write the equations down and then we'll analyze it. The other thing we'll talk about in this particular section is doing problems with friction. Okay, we'll do rolling and sliding friction. So let's get started. Okay, it's the same setup. This is the same figure I drew earlier. This is a body acted upon by a rigid body acted upon by forces, moments. G is the center of mass. Okay, but unlike the previous section, there's no point on this body where this body rotates about. So there is no fixed point. Just like a pendulum, there's a fixed point about which this body rotates. There's no such fixed point. So in such a case, the equations of motion are fx equals max, fy equals may, and if you want, you can take the moments about g. It's ig alpha. So if you go back and turn pages and see the equations for the fixed axis case, you see the same equations. So this is same equations as 17.4. There's no change. However, as I said, sometimes you want to analyze this rigid body about a different point. You want to take moments about a different point. And the reason for taking moments about a different point are that at some points there are reaction forces, and you do not want the reaction forces to appear in the equation, so you'll take moments about a different point. So if you like, you can also find the equations of motion another way. So you'll have fx equals max, fy equals may, and then let's assume there's an arbitrary point P, okay? And you want to take the moments about point P, okay? Point P is not fixed like the previous problem. It's not fixed. So m at P is equal to Ig times alpha plus, okay, I'm going to sort of abuse notation here. Well, let me do it this way. I'm going to write this as a vector. This is a vector. So you know that alpha, since this is planar motion, alpha is always in the k direction. So that vector is always in the k direction. The reason I wrote that as a vector is because there's no other way for me to write this part. So the last part, this part of the equation is basically the moment due to acceleration. So if mass time acceleration is the inertial forces, right, due to acceleration, then in order to find the moment due to that part, you need to take the vector from P to G, vector from P to G, and then take the cross product with mass times acceleration. Again, it'll become clear when I solve the problem. So the key is, this is different from 17.4. Okay. In 17.4, what we had done was, if the point P is fixed, that is, its rotation about a fixed axis like a pendulum, then we had dropped this term and we had said this is I about P, right? Inertia about P can be found by using parallel axis theorem. But when you have a case when point P is, or any point, the point about which you're taking moments is not fixed, you cannot take IP. You have to do this equation. This is more complicated than what we've seen before. Yeah? Because it's the acceleration of the center of mass. G is this point. Okay, so that's one thing. The other thing I want to talk about is friction, and then we'll get to problems. Okay, so in real world, it's very difficult to have a non-frictionless surface. You can get close to zero friction, but you cannot eliminate it. So if you have a block which is placed on the table, and if I start applying a force, then there's going to be friction, and friction is always going to oppose motion. It will not help you to move. It will always prevent you from moving. Now, the way we model friction, and again, this is a computational model, is that friction is best represented by what is known as Coulomb friction. So, friction model is, if Ff is the friction, then it is mu s times the normal force. So, what I mean by normal force is, if I draw the free body diagram, this is F, this is mg n. The friction force is going to be in the direction which is opposite to the impending motion. So in this case, F, the application of F makes it move to the right. The other thing you got to know is Ff is mu k times n is okay. So I've written down a formula for Ff. I've written down it as mu s times n. I've also written it down as mu k times n. So which formula do you use? Well, it turns out depends on the situation. So if you are applying a force F and you keep increasing F, well, when F is zero, clearly nothing moves. As you keep increasing F, you'll see that at some point the block starts moving to the right. Okay, the force needed to make the block to move to the right depends on mu s. So when F becomes equal to Ff equals mu s n, block will start moving. However, once you get into motion, what acts is not the static friction but the kinetic friction. So F minus Ff equals ma, or F minus mu kn equals ma. Block is moving. So this is v equals 0. When the velocity of the block is 0, you got to use F equals mu times n. When F equals mu times n, that's when the block will initiate motion, and the rest of the time when v is greater than 0, you got to apply the other equation. Okay, so that is what is known as sliding friction. So the block is sliding, and that's why that's the formula you got to use. Now you could also have a case where there is a circular disk and the circular disk is spinning. right? That also is subject to friction forces. So next thing I'm going to talk about is the rolling versus slipping of a wheel. So now I replace the block with a wheel. There's force, there is a normal force. There's mg, okay, and the friction force is going to oppose motion. So the difference between sliding block and rolling wheel is that for sliding block, you're only interested in linear motion. So you just have, it's like a particle motion. You only have fx equals max and fy equals may. But in case of a rolling wheel, you not only have the translation, in this case about x and y, well, y is clearly 0, but it also has rolling motion. So you got to use the moment equation too. Now, depending on the friction force, you can get, you can get three cases. Again, this is where it gets complicated. If the wheel is purely rolling, okay, how do you figure out if a wheel is rolling? You'll see that the contact point, so I'll call this the contact point P, has a zero speed. Okay, in this case, the friction force is always going to be less than the coefficient of static friction times n. Okay, what is true is that v equals omega. So if this is capital R, the radius of the wheel, then v equals omega r, where v is the speed, v and a is velocity and acceleration, and then omega and alpha is the angular speed and angular acceleration. Then v equals omega r and a equals alpha r. When I say v, it's really v of, okay, let me call this point, the center as g. So g is the center. So when I say velocity, I really mean velocity of g and acceleration of g. Okay. So when you drive a car, normal circumstances, nice smooth road, your car is rolling. It's not slipping. Slipping is very uncomfortable situation, right? When you're sliding like on ice. So slip impending. So when does that happen? So slip impending happens when F, the friction force, equals mu Sn. So if you place your leg too hard on the accelerator or on the brake, then you'll have friction. You'll have, well, the friction force becomes equal to mu s times n, and then you'll have slip impending. So that is the point where the slip initiates. Then there is actual slipping or sliding. This is when F equals mu Kn. So this is very similar to the previous case, right? Similar to sliding block. So for a sliding block, remember I said friction force is mu Sn, that's when slip initiates, and then when it's actually slipping, then the friction is mu k times n. So one of the, I would say, standard problem which you can hope to see either in the exam or in the homework is that of circular disc is acted upon by a moment. Okay, that moment m could be the motor which is making the wheel spin. So like in a car, or it could be a wheel which is subjected to a pushing force F. So you can expect, well, you could see a problem like this where you could either have a moment m or a force F, and you're told to find, pretty much you're told to find friction forces, you're told to find the acceleration and find the linear angular acceleration, and sometimes you're also asked to find if it's slipping or not slipping. Yeah?
You said earlier, like, smooth surface.
This is not smooth, no.
I'm saying, if it was smooth surface, would that be...
Oh, smooth, then FF goes away. So your life is much easier. Yeah, then if the smooth surface, I would just throw this out.
I'm saying if it's slipping or rolling, it's a smooth surface.
If it's smooth surface, then you will not have.
You don't have to worry about this.
Well, so what you will see is the problem later in the chapter where when you want to initiate motion, when you start rolling, actually friction helps you to start rolling. So when you step on the gas pedal, it's actually the friction force which is helping you to spin the wheel. If there's no friction, then things are going to slide.
Okay, so when it's slipping, it's not good.
No, you cannot say from this if it's slipping or not, no. So when I draw this figures, it doesn't mean that this is slipping because that's when the friction force. What I've only told you is when it's rolling, the friction force is less than mu Sn. Okay, so how do we solve problems? I'm getting to that. So when you're solving problems, you could get two types of problems. One is you're told it is rolling. The wheel rolls. So in that case, you can just solve it, set up equations and solve it. You can assume Ff is less than mu Sn, take those conditions and solve it. That's much easier. But another line of problems is you're given a problem, you're given F, you're given mg, and you're told to find, analyze the motion. So in that case, you do not know if it's slipping or if it's rolling. And the way to solve this problem is always, and there's no escape from this, you have to first start assuming it is rolling. Start solving the problem assuming it's rolling. You solve the problem, find the friction force. If you find that the friction force after doing the computation is less than mu Sn, your assumption is right, and you solve the problem. What will happen if Ff is greater than mu Sn, then your assumption that this rolling is incorrect. And then you will start all over again, solve the problem, assuming it's slipping and solve it. So I'm going to do a problem like this. That's why this is very hard, because it's not like you can just plug in and solve it. So here is a problem which will illustrate this best. And I'm going to try to finish this because this is very important. So it's the same recipe, free body diagram, equations of motion, kinematics. A 20 kg wheel has a radius of 0.1 meters. The coefficient of static and kinetic friction is mu s and mu k as given. If F is 300 newtons, find the acceleration to the center of mass. Assume G is 10. Okay, let's solve this. So the first part is pretty simple, straightforward, FBD. I've shown you how to draw the FBD. Show F, show N, show mg, show the friction force. Okay, friction force opposes motion, so that's right. Now, when I'm setting up the equations, I have to first, so you're not told here if it's rolling or sliding. You have to start assuming it's rolling. So assume wheel rolls. So again, the same three equations hold: fx, fy, and a moment. So fx equals ma. I'm going to write this with the subscript g. I need that. Let me write agx, so it's very clear that it's the acceleration of point g. So this gives me, so all the forces in the x direction equals mass times acceleration. So F minus F equals mass times A. I'm going to write A now because this wheel, even if it's spinning or rolling, will not have acceleration in the y direction. It can only have acceleration in the x direction. So that's that. Fy is mass times AGY. That gives me normal force minus mg equals mass times acceleration, but the acceleration is in the y direction is 0 because it's not flying in the air, right? And then the final equation is moment about, you can take moment about any point you like. You can take moment about g, you can take moment about the contact point, okay? You can take moment about any other point. But what makes sense here is either g or point of contact. I'm going to just take about g because that's the simplest thing. I need to solve for ff, so I'm going to take it about g. So this gives me the moment about g, this point. The effect of n, mg, and f has, well, they have no effect on moment about g because the line of action is through g. The only thing which will create a moment is ff, right? So if I hold the disk at g and apply ff, then it's going to make the disk spin in the clockwise direction. So minus ff times r equals ig alpha. Now this is something which will give you, ig turns out to be half mr square alpha. We'll give it to you, yeah. We'll give you mr square divided by 2. We'll give it to you. Okay, so let's count the equations. So 3 equations, and the unknowns are ff, a, alpha, okay, and n. So you cannot solve for 4 unknowns with 3 equations. So you need a 4th equation. So the 4th equation is from kinematics. A equals alpha r. Okay. Condition for rolling. So now I have 4 equations, 4 unknowns. So, okay, I'm going to skip how I solve for it, but you can clearly solve for the 4 unknowns. So, solving gives me f equals, well, I got this, fa equals alpha. I also got na equals 200, and I also got f equals, sorry, fa equals f divided by 3, which is equal to 100 newtons. So what I was after is, this is ff, my bad. I was after ff because I want to check if this is rolling or slipping. So ff is 100 newtons, and if you try to find mu s times n, this is equal to, mu s is 0.3 times n is 10 times 20, so 200, which is, I think it's 66.7. You know what that comes out to be? It's 60. Sorry, 60. Okay, so 100 is greater than 60. Right? What it's saying is that the friction force is greater than mu s times n. If you get a condition where friction force is greater than, so this is the condition for rolling, the friction force should be less than mu s n. What I got is friction force is greater than mu s n, or 100 is greater than 60, which means it is not rolling. So my assumption was wrong. So then I have to resolve the problem assuming it's slipping. So going back, yeah.
Why don't you put friction force equal to alpha?
Oh, I did not put. This is solved. I get it to be Ff equals alpha when I solve this from this equation actually. When I sub in the value for m, r, etc., I get that. I think you get a negative or something like that. Yeah, you get a negative alpha, sorry. Yeah, but you can put the values and you get that. Okay, so then what I do is I go back, I say, assume, now I know for sure it slips, so disk is slipping. So the good thing about when the disk is slipping is you do not have to write the equations all over again. Three of these equations are the same. F minus ff is ma, n minus mg equals 0, and minus ff times r equals half mr square alpha, same equations. Okay, so those equations are the same. You do not have to change them. This equation is not true. A is not equal to alpha times r. That is not true because it's slipping. The way you solve this is, again, you have three equations and four unknowns. So you need to generate the fourth equation. Remember that previously the fourth equation came from this, and we do not have that. So the fourth equation actually comes from friction condition. Ff is equal to mu k times n. So that is your fourth condition. That's the fourth equation. So give me like 30 seconds, I'm done. 2, 3, 4. 4 equations and 4 unknowns. If I solve this, I get A, G. Solving gives me FF is FF is 40 newtons. AG is 13 meters per second square. Yeah, I think I did not solve for alpha, but you can solve for, well, alpha is 40 radians per second square. Yeah, so this will be negative. This will also be negative because so this is, my bad, this is 13, that's right, but this is going to be negative because it's clockwise. So that's it. So as I said, this is a very important problem because in the past we have given this problem once in the term exam, once in the finals, hoping that people who would solve this problem in the term exam would do well in the finals on the same problem, but surprisingly many people got it wrong both times. So students don't just learn, they just don't look at their exams, but this is